Okay, so now I'm going to talk about developments in computation and the computer, or specifically the Turing machine. So, before the advent of computers, one of the things that needed to be resolved, at least to some extent, was called the decision problem. And the decision problem is this: is there a formal method to figure out whether a problem is computable or answerable or not? Right? So, is there a formal method to figure out whether a problem is answerable or not? Right? Are there some problems that we will never be able to solve that just cannot be answered? And if so, is there a program or a method to figure out whether it could be computed or not? And so, uh, yeah, Alan Turing was a mathematician slash logician. He's also the father of modern computer science. And he set up a different version of the decision problem called the halting problem. And the halting problem is basically this. If you're given a program in some formal language, when I say formal language, I mean a logic-based or programming language. And so if you're given a program in some formal language, is there a method that will tell us whether the program will halt or not? And so, yeah, is there a program and a program halts when it's been successfully executed, right? So when the problem has been successfully solved, then the program halts because it's done doing what it was supposed to do, which is find an answer. So you want it to halt, right? That's the big thing. You want it to halt because then it means that it solved the problem. Yeah, so I'm a very inefficient programmer, for example, because I'm a psychologist. And so I might have like 1,000 lines of code to do something that a real programmer could do in probably a tenth of what I did. So 100 lines of code instead of 1,000 lines of code. Now, because my programs can be super inefficient sometimes, it will take a while for those programs to run. So when I run the program, it'll take a while and I'll see that the program is initializing and then keeps running. It's still running. It's still running. And the question is the program ever going to halt or solve the problem or do what I asked it to do successfully? Is it going to successfully execute the problem? Or is it just going to keep running forever and ever and try to find an answer that can never be solved? Uh, yeah, so where the answer doesn't actually exist. And so Alan Turing showed that some problems are not computable. And he did this using what's called a Turing machine, which we'll talk about more in the first wave of cognitive science. He also showed that some problems are not computable, right? Which is, I think that's actually just what I said. Uh, yeah, sorry. Yeah, and then he introduced the idea of an algorithm to solve computable problems. Now, when I say algorithm, I don't mean algorithm in the way that everybody thinks of algorithms, which is ways in which which social media capitalizes on your attention. I'm talking about an algorithm, meaning like a set of steps that you can take in order to get to an answer, if you follow it perfectly, if you follow the steps perfectly. You can think of an algorithm as kind of like a recipe. When you're making something or cooking something, a recipe is kind of an algorithm with the qualification, of course, that you can mess up a recipe, right? Here, though, this is one in which if you follow the steps correctly, you will definitely get to the answer if there is one, which we do all the time with math problems, right? So when you add two numbers, right? You list them vertically, one on top of the other, and then you add the ones column, and then you maybe carry whatever is left, and then you like the one, for example, if it's greater than nine, you carry the one, and then you add the one to the tens columns, which you also add the tens columns. This is just an algorithm, right? It's a series of steps that you take in order to solve a problem, in this case, an addition problem. Okay. And so this algorithm is a finite set of rules that would guarantee the correct answer if followed correctly. He also developed what's called a Turing machine. He didn't call it that, but it became known as a Turing machine. And these Turing machines are essentially idealized abstract computers. So they're not real machines, okay? But with this, he showed that computation can be done in a purely mechanical way. And by doing this, he laid the groundwork for the invention of computers. It also helped spawn the idea of the mind as a computer framework, thinking about how the mind works and looking at a computer for guidance about how the mind works. This also helped show how information could be processed by the mind. Yeah, and so finally, he introduced the idea, as I said, he introduced the idea of an algorithm, which is a really important concept for cognitive science. Okay, so we'll talk more about this later. This is just sort of a brief cursory discussion of the theory of computation because we're talking about catalysts for cognitive science. Yeah, and so in the next video, we'll talk about Noam Chomsky's critique of behaviorism as well as transformational grammar.